Hi, class. I hope that you're doing well and that you're staying safe and that nobody has caught any viruses or anything. Today we're taking a look at linear correlation, which is Unit C. I've got the manual here in a PDF form, and I'm just going to write right on top of it, so it should match your book perfectly. So this is page 133 of your book, and it's Unit C1 on linear correlation. Now, let's talk about what we're looking at here with linear correlation. We're moving into the last main section of the course here. And remember that 307 is looking at, in particular, how variables interact with each other. So one variable versus another variable, is there a relationship between them? And we looked at three main types of problems here. So we've got nominal versus nominal. Now that would be something like, let's say you have a question such as, do you agree with this particular proposition, yes or no? And then you've got gender. And you want to ask, is there a relationship between the two? Well, that, of course, would be a test of independence. The second type of problem that we looked at, which was in Unit A and also in T, is where you've got nominal versus interval, nominal versus interval. So that would be something like, well, what town do you come from and what is your age? So you've got town, which is nominal, and you've got age, which is interval, and that would be an ANOVA test. Now, of course, you would want to take a look at the conditions of ANOVA and make sure that normality holds, that the homogeneity of variances holds, and if they don't, then you'd want to be using a Kruskal-Wallis test. A Kruskal-Wallis test is also used when we're talking about nominal versus ordinal. So let's say we're asking the question, is there a gender difference? So gender would be nominal, versus a rating scale, how people feel about a particular movie, rated on a 5-point scale. So nominal versus ordinal, right away you would go to a Kruskal-Wallis test. Now, we also looked at t-tests, which is two-sample t-tests where you only have two treatments, like yes, no, that kind of thing. And take a look at that particular one. We've already gone through that, and that was on your second exam here. But we're moving into the third main area here, which is interval versus interval. So that might be something like, what determines the selling price of a house? So selling price of a house, of course, is interval in nature. And we might look at variables such as the size of the house in square feet, the age of the house in years, the number of bedrooms, the number of bathrooms, and so on. So those are interval variables. Interval versus interval means that we're talking about regression. And here we're talking about units C, S, M. So C stands for linear correlation. That's this particular unit here. And it's the fundamental building block of regression. And then we'll look at simple linear regression, where you have one X and one Y variable. And then multiple linear regression, which is dealing with one Y variable, and then a bunch of X variables. So let's continue on here then, and we're going to dive into section C here. Just going to scroll up like this. There we go. So I'm on page C1. We're going to go from C1 to C4 in this particular lesson. And I'm on page 135 here. Now there's an opening paragraph here that says that often people tend to use the term correlation rather loosely. So I might say, I wonder if there's a relationship, a correlation between the gender of a person and their age or something like this, or their rating on a movie. Well, those two variables then are not interval in nature. So in statistics, when we talk about linear correlation, we're looking at the linear relationship between two interval scale variables, like the price of the house and the size of the house in square feet. And later we'll see that we can draw a regression line which describes that relationship. So that's what we mean by correlation. We'll be looking at two specific tests in this unit, we'll be looking at something called the Pearson's linear correlation. And that's the standard one. That's where you've got two interval scale variables and that the condition of normality holds. However, if normality fails for one or both of the variables, or if one or both of the variables are ordinal in nature, then we would be using a Spearman's non-parametric test. So it's the same kind of relationship that we had with ANOVA versus Kruskal-Wallis. So ANOVA and Pearson's linear correlation are the parametric tests using interval scale variables. But if the conditions fail, or one or both of the variables are ordinal in nature, then we're talking about a non-parametric test called Spearman's, which is like a Kruskal-Wallis back in ANOVA. All right, let's take a look at a really important new concept here, a new term. This is called the population correlation coefficient. And it is a measure of the linear relationship between two variables, x and y. So take a look at this particular listing of numbers that I've got down here. I've got the height and the weight of respondents, and you'll notice that both of them are interval in nature. The other important thing to note is that they're paired. So this is, say, respondent number 1, and of course if this were a data table, you'd have everything in a particular row corresponds to respondent number 1. So a height is paired with a weight. It's important that when you sort the data set according to height, and you might want to do that to check to see that you have no missing values. So you sort according to the height, and then you go down to the very bottom of the list here, and you check and see if there's any missing cells or blank cells for either the height or the weight. And if there were, then you would delete that particular row. And then you would do the same for weight. And so you sort according to weight, making sure that the height set sorts with it. And then you go down to the very bottom and you check to see if there's any blank values. And you would get rid of any rows that don't have both a height and a weight. So when you're ready to go, you'd have a listing of x's and corresponding weights, or y's in this particular case. So x and y, height and weight. All right, let's continue on here. The measure that we have for the relationship between these two is called the covariance of x and y. And it's actually shown by this formula right here. So it's how the x's vary with the y's. Now, this is actually really similar to a formula that you know quite well. This is the variance of x. And of course, we would write it this way, but you could say it's how x varies with itself, although people never use that subscript like that. And we could expand out the top here like this. So x minus mu times x minus mu. So you can see how that's very similar in form to this here, except that we're talking about how the x's correspond to the y's. So they're variance here. So it's a measure of variance. It's called a covariance of x and y. Now the problem with the covariance of x and y is that we can't really tell whether it's high or low unless we know the units that we're dealing with. So if I said to you that the covariance of x and y is 20, was that high or low? And you say, well, I mean, it depends what we're talking about. If it's talking about house prices and size and so on, that's probably pretty low, right? So what we do is we standardize this by dividing the covariance of x and y by the standard deviation of x and the standard deviation of y. And that has a special name. It's called rho, the population correlation coefficient. And rho, which is pronounced like that, rho, is actually the 17th letter of the Greek alphabet, and we draw it as kind of a stylized P. It's actually where we get our R from. You'd think it's where we get our P from, but we actually get that from pi. But it's drawn as a stylized P. And so that's rho. And I'm just going to expand this out here and say, so the covariance of x and y would be the sum of the x's minus the mean of the x's, I'll just use a little subscript there under the mu, times y minus the mean of the y's over n. And then, of course, in the denominator, we just have our regular formula here for standard deviations. So you'd have the standard deviation of x and the standard deviation of y. So that is the covariance, that's the population correlation coefficient, or rho, and it's a measure of the relationship between the two. Now, the nice thing about this is that rho takes on values of -1 to +1. We'll see this again at the bottom of this page. So I'm on page C3 here. And I want to take a look at rows that are -1, +1, and 0. Let's start with a row of +1. So a row of +1 occurs when you end up with an x and a y which are perfectly positively correlated. Oops, that's a y, not an x. There we go. So let's say we've got the following. We've got 1, 2, 3, 4, and 5, 4, 8, 12, 16, and 20. Again, sorry for the messiness, but it's hard to write on glass. And if we were to plot these out, this is what we'd end up with, is we'd end up with all of the points on a straight line like this. So we could draw a line between them like that, and you could see that all of the points are on a positive sloped line. It doesn't have to pass through the origin as long as it's positively sloped. If all the points are on a positive sloped line, then we say that the rho is equal to +1. So that's a perfect positive correlation. Perfect negative correlation is easy to figure out. That, of course, would be where you end up with x, y. I'm not going to plot out all of these numbers in this particular case, but what you'd end up with is all of the x's would be on a line that would be negatively sloped. Okay, so it's a negatively sloped line. All of the points are on the line. That is a row of -1. Then we've got a row equal to 0. Now I'm going to show you 3 cases actually of a row equal to 0. This first case here is where we have actually a pretty nice looking line here. You've got a y value of 8, and all the points are actually on a horizontal line. But when you think about that, what that's saying is that you can increase or decrease x and it has no effect on y. So that means that the correlation is 0. Here's 2 other scenarios down here. In this first one, what we have is, and again, I'm not going to plot out all these things, but what you would end up with is just a scattering of points that don't seem to have any particular positive or negative relationship between them. So if I tried to draw a line through this mess, would it be positive? Would it be negative? Don't know. And so what happens then is that when you stick in the formulas and so on like this, you end up with a line that goes like that. So it has a slope equal to 0, and so we would say that that's a rho equal to 0. If you haven't noted by now, you'll note that the sign of the correlation coefficient, whether it's positive or negative, completely corresponds with the sign of the slope. And so in this case then, we have a slope equal to 0. Here's the last case, and that is where you might actually have a fairly strong relationship between x and y, but it's not a linear one. So in this particular example, if we were to plot out these points, we'd end up with something like this. So a strong relationship, but it's not a linear one. Or it could be, of course, quadratic. It could be some other relationship between the two, logarithmic or something like that, but it's not linear. And so again, we would end up with really a regression line that looks like that. So what we have here then is that rho goes from -1 to +1. Okay, let's end this off on page C4 by working through the example that we had here. Now the problem is, of course, is that we don't have access to the whole population, and so we have to take a sample. And when you're dealing with a sample then, you're not dealing with rho, we're actually dealing with the sample equivalent, which is called R. So R then is the sample statistic which estimates rho, just like x bar is used to estimate mu, and s squared is used to estimate sigma squared. So R is a sample statistic, and you'll notice that it's based on sample values, which are x bar and y bar and little n's. And if we take a look over here, it's the sample covariance of x and y divided by the sample standard deviation of x and the sample standard deviation of y. Now that's kind of an ugly formula up here. This one's a little better computationally. It's still ugly. It's about the ugliest formula you're going to get in this particular course. But that's what the thing looks like. And just like rho has a range from -1 to +1, so does R. So let's take a look at our example here of height and weight. So the original columns then give you the heights and the weights, and that's going to be the x's and the y's. We can sum these up, and we'll get these numbers here. So 654, and that's going to be the sum of the x's. And then the y sum up to 1720, so that's the sum of the y's. The x squares are found by taking each x value and squaring it. So this particular first number here is 3136, and that would be 56 squared. Now, if we took 95 and squared it, which is the first y value, we'd end up with 9025. And then if we took the x times the y, so this would be 56 times 95, and you'd end up with 5320. Now, I'm not going to fill in all of these numbers here. You can do that just as well as I can. But I will give you the sums down here. So you do that for every row. So 57 across times 57 gives you that number. 145 squared gives you that number. And then 57 times 145 gives you that number, and so on. Sum them all up, and you'll end up with the following numbers here. So 43,132, and we call that the sum of the squared x's. And then the sum of the squared y's is 315,300, so that's the sum of the y squares. And then finally, the sum of the xy's is 114,860. That's a 4 right there. Okay, so that's the sum of the xy's. All right, let's calculate now R using these particular values. So R is equal to the sum of the x's times the sum of the y's minus, no, it's not. That's what happens when you haven't done this for a while. Okay, let's try that again. All right, so the formula here, here we go. It's the sum of the xy's minus the sum of the x's, sum of the y's over n, and then divided by standard deviations, or a variation of them anyways. So the sum of the x squares minus the square of the sum of x's over n, and then the same for the y's. So the sum of the y squares minus the square of the sum of y over n. So let me show you when we plug in the numbers here. Sum of the xy's is 114, 860, and then minus 654 times 1720, and that's over 10. Now, two things I want you to note is that this 10 is only only in the last term here. So you don't divide the 114, 860 divided by 10. And the other really important thing here, and this is a common mistake that people make, is that there's actually 20 numbers here, but there's 10 respondents, so 10 pairings. So 10 is the number of x's, and of course you'll have corresponding 10 y's. So it's the number of respondents, or the number of pairs. Okay, the denominator is going to be the sum of the x squared values, so that's going to be 43,132 minus the square of the sum of x's, so 654 squared, divide that by 10, and then we do the same for y. So the sum of the y squares is 315,300 minus 1720, that's a 7, doesn't look like it, squared over 10. And when the smoke clears, you end up with positive 0.896. There we go. Now, that is a very high positive correlation. That's really close to +1. So what we're saying here then is that there is a strong positive correlation between x and y. The problem is that although in this one it's fairly obvious that there's a strong positive correlation, you can't say that with every problem. So you can actually have a strong positive correlation that ends up with an R of 0.1, but if you had a sample size of, say, 1,000, that could actually be very strong and therefore significant. And so at that point, I'm going to end the lesson, and we're going to pick that up later on the hypothesis tests.